follow the internet, there's some challenges and implementations and asymmetric gigabit internet-based networks. Is working with reliability.
Are at the moment our topic. Essentially, the entire asymmetric Ethernet direction is motivated by this kind of architecture, where there is some central processing element and zonal switches and different video and radar data is aggregated and then sent eventually to some central processing. Some big driving factors or motivating factors are raw data, the enablement of software-defined features, and also sensor fusion. So, for instance, something which is very attractive is to aggregate different radars mechanisms and then fuse all the information together in some central box. Some other advantages of this is then less boxes with the software box for easier updates, reduction of cables, shorter cables, less connectors. The trend, let's see how this eventually turns out, is all Ethernet. So a lot of this talk or assumptions in this talk are based on the all the eventually Ethernet assumption. It means that the layer 2 and above is then Ethernet or video and the physical layers are then, for instance, something like the DM or something which is capable of transport. So the kind of landscape that we have specifically for sensors right now is driven by a lot of proprietary standards. So I depicted here two kind of use cases. So one thing is a radar kind of use case where you typically have some radar DSP and then directly connected with some radar sensors. By the way, this is just an example. I'm not saying there are always all radar sensors. That is just an information. And then these are usually some short-range connections, so like CSI2 for instance, and then the actual radar information, object streams, and then communicated either over some N variant or megabit or megabit Ethernet to some processing. The video use case, video sensors is at the moment typically done in this kind of fashion. So there is some camera with some character service solution, and there are a couple of different flavors of this, and then some deserialization, some ISP processing, and then eventually some switches. We all know that there are these discussions regarding asymmetric Ethernet. There are a couple of physics layers and discussions. I won't go over this talk. The assumption is that there is some asymmetric physical layer available, and we are looking at more some sort. So the kind of short-reach streaming interfaces, for instance, these guys here, or something like here, these are typically at the moment variants of maybe CSI2, C5D5 or DSI type. And then there are some other sensors which I'm not really talking about because they are in this context of infrastructure. Those data sensors like actuators, door locks or something like this, which are then connected over something or some close interfaces. So now that we talk about these kind of interfaces, this is in my vision on the evolution of how this could be. I'm not saying this is the way how it really works, it's just a potential way. So we start off with something like this, where for the SoCs we typically have some CSI streaming interface, and then at the moment we go to some proprietary service streaming, and then the next step would be, you see this already with go to the exhibition booth. There are some Ethernet bridges or some specifically Ethernet. There are also other solutions, but here our assumption is we want to be more Ethernet, so it's the next step to bridge between CSI2 and some sort of T1 or coax solution. And then the ultimate incarnation is then to essentially up-integrate portions of this. For instance, then have these encapsulation directly, encapsulation in this case, directly up-integrated to the system. And then similarly, it's more or less the same kind of storyline for the sensors. So at the moment, it's driven by some SOLI solution. We go into the Ethernet bridge solution, which you see on display. And then eventually, you up-integrate something like a static encapsulation scheme in your imager with some sort of SOLI's interface and write it into a file. And here, there's a lot of debate in which direction it goes. Some people say, well, you can also up-integrate asymmetric files entry into an imager, depending on the actual power dissipation of the solution. So this is kind of last step will probably depend a bit how this their discussion turns out. My assumption at the moment is that the overall power consumption might be too high, certainly for things like, for instance, radars, which are susceptible to noise levels and temperature increases and the quality keeps degrading. So it's a bit of a unclear situation. What is integrated eventually in the next 10 to 15 or so years. So, assuming that this is the kind of long-term evolution, then the obvious next step is to make these first transitions happen. And this is what we are going to talk about today. So, in order to make this happen, essentially, the kind of protocols that are needed for sensor communication schemes need to be able to transfer CSI2 data, as well as also some sort of communication, communication along Ethernet. So what do we actually, or in order to write this, what do we need to enable encapsulate or communicate over Ethernet in order to write and make this work? So we already discussed about something like S.C. This is usually used to configure certain camera modes, brightness control, also set some pixel formats up. So it's typically a communication control scheme. Then there are some GPIO pins like resets. There are some time synchronous pins which are relevant to synchronize shutter events and also for radar. It's conceptually very similar. There is a signal called shutter start, which is synchronizing the radar sensors to synchronize them. They are starting with the shutter at the same instant and allows, this is very tightly synchronized, allows to aggregate any different radar information data sets into one synthetic radar image, so to say. And then eventually you have the actual streaming data which is coming out, which is mostly CSI2 based. Regarding timing information, so to drive these things that should start the testing, there are already some protocols available in the entire TFN spectrum, which I'm not going into detail here, versus, for instance, the PTP mechanism, which is able to recover time and driving the S-symbol with some really slight technical distinction. So this is the overall protocol stack which might be used to drive this technology. So on layer 1, the assumption is the Ethernet. Then on top you have some quality service control, VLANs, aggregation, MACsec for encryption, and then the actual streaming data is encapsulated in the 722 transport. And then on top of this, and this is the details here of this presentation, is then what is generic image sensor format, as well as control data in the form of tunneling of I2C. There's another thing which we will talk about more in detail called generic bypass. And there are some other mechanisms to communicate GPIO status and essentially remotely follow things over this problem. The interesting thing is that so far you probably have seen there is no mentioning of CSI directly in 1722. This is done in the Alliance, and I can't really talk a lot about the fundamental details about this. The way how it does is essentially it's encapsulating CSI2 into this generic image streaming format. A bit of piggybacking on the mechanism will look into details roughly how it roughly works. And the remaining portions here are driven in 1722. So let's first look at I2C encapsulation. Now this works in detail, how it comes together, and what it supports, and what the problems are, and what the advantages. So the kind of idea behind this is to first start off with a traditional way how I2C works. We have an initiator device, and typically on the same PCB have connected some target device or directly over some PCB traces. The kind of thing that we want to do now is we want to break this and have some bridge mechanism so that's we want to come from here and do it here. The assumption here is that the mechanism is to basically transmit and receive the entire thing through Ethernet, so that neither the initiator nor the target really know that there's something in between. It should just look like an extension point, essentially. So the way how I2C works for those that don't know the protocol is that there is some start condition mechanism so that the target knows when the transaction starts, some address bits, some indication if it is a write transaction, and it comes to acknowledge, and then a payload byte, and then there's another acknowledge, payload byte, another acknowledge. Depending on where you are on this frame, some of these acknowledges come from one side, and the other acknowledges come from the other side, so it's a bidirectional mechanism over the SDA's data. And the challenge of the protocol is in the obvious way, or the obvious question is why not just taking all this address and bytes and put this into Ethernet frame, send it over, and just use this information. The problem is that you can't really do this because you don't know the state of the acknowledges in advance. So essentially to make this work, you need to undergo the I2C translation on the fly over Ethernet. And this results in some sort of event by event driven scheme, where each of these big events result in its own Ethernet. So the way how this looks is depicted here in this super small example. So each I2C event, what an event is, you just need to trust me. Each I2C event is resulting in its own kind of Ethernet frame, which is then sent from the initiator through Ethernet to the other side, and then another event on the other side is then generated, and another frame is sent in the opposite direction. So for this kind of example scenario where you have some address bits, something byte, then 2 payload bytes, this results into these 7 Ethernet frames being sent back. So this is a frame which is sent then into direction towards the receiving side, and this acknowledged then comes essentially back in the opposite direction. So the advantage of this scheme is that it works transparently and it works. The disadvantage is, and you can see this already, it adds some overhead. So the number of frames that you need to drive this relatively simple thing is 7, and because of the MTU requirement, that boils it already down to 448 bytes. So now I know there's a bit of discussion, but I don't want to really go into all the asymmetric DM kind of discussions that are already happening in IEEE. Depending a bit how your slow decorate works, this latency might be okay or might not be okay. But it's making it this way with the back and forth action is really the only way to make it fully transparent. just to get an idea of what we are talking about, and for a proper example, I included some numbers that are actually taken or Wireshark from the demo that we see in our group, where we have some level imaging camera connected to some bridging device, and on the other side there's some images that are showing this thing. And by just Wiresharking the frames going back and forth, I know that the initialization of this imager is resides in roughly 1.5 kilobytes of S2C data, including everything like address gigabytes. And this then resides into roughly 3.5K frames and 251 kilobytes of total T1 data. So the overhead is really quite big. And depending a bit on the topologies on the switches you have in between, what the link speeds are, this may or not be a problem. If you just run everything through 10K in both directions, there's nobody really fast. But if the slow direction has some latency or some intrinsic latency or increased intrinsic latency, and there are multiple also switches in between, this may be a problem to then start up the camera and time essentially. Now the question is, and there are some other advanced topics which I'm not really going into detail. So one thing is, which you probably might think of first, frames are going back and forth, and how does then the target throttle the initiator to make it wait? But there's a mechanism called clock stretching, which is driving the back pressure. It's interestingly, in the I2C spec itself, clock stretching is optional. So, to my knowledge, as of my knowledge, the cameras and everything which is driving is really use case. Everything supports this scheme, so it's not really a problem. This clock stretching thing is the optional feature. But per se, it's optional, so you can't really drive each and every different mechanism of this technically. And then there's also some error recovery mechanism built into the spec, which allows the mechanism to recover from the speed. So now I talked about this I2C encapsulation, but I also highlighted the overhead, which is somewhat motivating already. This isn't good enough. But I2B, especially in 1722, thought already about solution, which is called generic bypass. So the idea is generic bypass is it removes the overhead of this I2C, and it's able to carry the entire transaction completely in one big Ethernet frame, or one big 732 frame across the network. And it even can chain and multiple transactions in one big message, which potentially allows you to implement how big these virtualization instances are. To pack everything together and then have just one file and forget kind of thing, which sets everything up. And given the ANTU allows all systems to be different. But efficiency-wise, this is the goal that makes it really fast. The drawback is not really able to faithfully replace I2C. So the way how this works is that the initiator side needs to drive this mechanism without necessarily any software or some hardware on the SoC to create one of these frames. They are then sent off as generic bypass frames at the other side, the receiving side. The targets like it's still able to essentially underlay or unload these frames only through the I2C. So one side is essentially the virtual I2C interface, on the other side is the physical. Okay, so now we talked about how the protocols work for control, specifically for I2C. Now let's look at the streaming side. So the thing is that there are some protocols in IEEE 1722 and there are other protocols in IEEE. And the relevant protocols in IEEE are essentially the CSV, which is a camera service extension, so kind of extension of the packaging format, and then the base CSI2 format. And then there is another protocol which I can't really talk a lot about, which is specifying how how exactly CSI2 is encapsulated inside 1722. So in the next kind of slides, I'm briefly trying to get the idea of how this works without telling a lot of details. Just to get the idea that in CSI there are short packets for control and long packets for the actual data. So this is how it looks like. And this kind of diagram is also publicly available. So you see that packets in the frame starts a short packet, and in long packets you have some sort of header information and some payload data, some footer, and then the stuff over. And the idea is essentially to take the kind of the CSI packets and segment them into smaller chunks. And then piggyback onto the format is 1722, which is called geographic interesting format, and transfer then the CSI2 data inside these GISF objects. Originally, the GISF format was intended to communicate really proper Axer data and has some fields which are, I would say, misused to communicate by some CSI2 over this. The way how this works is really relatively straightforward, and there are some fields in this GISF which are used to make this segmentation possible, like line numbers, some timestamps, and the stream ID to fuse it on the receiving side again, erase and back to the original CSI packets essentially. The actual encapsulation of this works in detail is a bit more complicated, but the idea is to slice them through package into 1722 headers, give them sequence numbers, and then after CSI essentially present it back to them. Now, an obvious question would be, isn't this adding a lot of overhead to the entire thing? Now I'm talking about 1722, where we have this, and 1722 knows that there are some additional headers involved, carrying potentially timestamps and some other control information, something like stream ID, which is already 64 bits. The question is, isn't this adding now additional overhead and then potentially requires to go to the next speed break or something? There is the nature of things, overhead, but there is also some real benefit by using this 1722 mechanism. The idea is that it comes with all the advantages of 1722 for free, essentially. You have the timestamps, which allows you to have presentation timestamps on all the frames, and also timestamp something like SLC messages, for instance, and you can put potentially, if you wanted to synchronize things over this mechanism, you put all these different things into one stream ID, and configure switches relatively straightforward to forward the different streams to the destination by just looking at the stream ID, and also prioritize them accordingly. So it all naturally falls into place, and it follows the kind of layer structure on top of it. So it seems logical. Also something which I'm not having on the list, but also that I run the numbers to see which order the overhead lies in. It's not a lot, especially if you're looking at 4K video or so. It's marginal. It's not really pushing it to the next speed break or something. So if you have a video which is below 5 gig, running it over 1722 won't make it suddenly a gigs or something. It will stay well within the same version. So let's come to the summary of the conclusion of this talk. So the protocol spec that we looked at allows to smooth